going to find him without them to catch him. Oh, okay. All right, so let's check these antirhythmics. Get mine out. Hopefully at one point you realize that some of them were formulas. Okay, so let's just go through the answers, and then the ones that stumped you, we'll go back and I'll explain, because some of them you probably got pretty easily. Okay, so the whole thing about the plus C is this is called, oh lordy, I'm blanking out on the name. It left me right now. Anyway, I don't have an order pair to plug in and find C. What's that called, Lily? When I can't find C, what's that word I can't think of? An integral. Indefinite integral. Whew, there we go. Okay, this is called an indefinite integral. When I don't have an order pair to plug in C. On the test, you had an order pair, you plugged it in, and you found your C value. So when we don't have that, we just always tack on that generic plus C. There could have been a number there. Its derivative was 0, therefore it doesn't show up in the derivative.
Oh, so we didn't have to find C.
You can't find C without more information.
We just plugged in 0.
Then you were being presumptuous. Yeah, so on these you can't find C. You can only find C if I give you a little more information, probably in the form of an order pair like we had on the test. So, yeah, we just leave it plus C. All right, so check number 1, 2, 3, 4. I think you can see through number 6 up there. Did 5 and 6 trip you up a little bit? Maybe 5, not as much as 6. Number 6 we need to come back to. Tell me the ones we need to come back to, but I want everybody to just check and see how they did first. Other than 6, any others so far?
8.
Well, hang on, I hadn't shown you the answer. Might have got it right. Okay, here's 7 and 8. Need to look at 8? Yeah. Okay. And the others on that first page that we need to explain. Now, how else could I write 2x to the 1/2? I stopped there, but did anybody else write it 2 square root of x? Okay, that's fine. But make sure the 2 is not under the radical, because the 2 is not raised to the 1/2, just the x. And all of these with exponents like this, with the 13/8. If you wanted to, you could make it the 8th root of x to the 13. That would be fine also. Okay, number 9, 10, 11, 12, 13, 14. Check your answers and just call out the ones that you need some explanation on. 11, okay. Any others that you need explanation? 14. Any others through 14? 13. Okay, let's slide it up. And there we go. Call out those that we need to talk about more in depth. $19. Everybody's good with 18? No, you're not. Oh, okay. Anything else? Hey, How'd you do on them overall? On a scale of 1 to 10. 8? Okay, I can live with that. First time throwing all these at you. Okay, so for a couple, you might have wanted to consult your formula sheet. Okay, so let me go back over to number 6, first of all. So did you have trouble with 5? Was that okay? Could you see that that was natural log? And if you can't, if you couldn't do 5, then 6 would certainly cause you trouble. So this is just straight up natural log. Whenever x is natural log of x. And then we tack on the plus c. Okay, this is nothing more than 5 times whenever x, right? And so this antiderivative is natural log. 5 is just a coefficient. So that means that our original function was 5 natural log x plus a constant. Okay. All right, let's jump down to 8. So what was the general rule? Like 3, that was pretty complex. What was your general rule that you were using to get the antiderivative? What'd you do with the exponent? Add 1. What'd you do instead of multiplying by that exponent? What'd you do to get the coefficient? Divide. Okay, so think about that rule here. Okay, so remember I told you you're going to get really good at adding fractions now. So if I add 1 to 5/8, that's the same as 8/8. So 5/8 plus 8/8 is 13/8. Okay, so I have a coefficient of -2. I'm going to have x to the 13/8, but then I'm going to divide by 13/8. Just your average little algebra number problem, right? Crazy numbers there. But dividing by 13/8 is the same as multiplying by the reciprocal, 8/13. Okay, so I would think of this as -2 times 8/13 x to the 13/8. And then that's really just 2/1, so we multiply straight across, and that gives me -16/13 x to the 13/8. And that was my original function. Now these are pretty easy to check. On this one you might want to use a calculator, but to check them, bring down the exponent, multiply by the coefficient, and subtract 1 from the exponent. And you should have what we started with. Any questions on that? So to skip one step, just remember, if you're going to divide by a fraction, it's the same as multiplying by its reciprocal. Okay, on the back. Oh, okay, so someone who was okay with this one, can you explain where this came from? It's the derivative of the exponent, which means we used what? Chain rule. Okay, so what did I have to start with? Well, first of all, derivative of e to something is e to that something, then times the derivative of the exponent. So if there's an e to the sine x here, that means we had to start with an e to the sine x, because it is its own derivative. But then when we multiplied by the derivative of the exponent, that's where that cosine came in. So that is the only function that we started with. So derivative is that times derivative of the exponent, which is why the cosine is there. So this is just chain rule that put that there. Does that make sense? I'll take that as a yes. Okay, so now look at 13. It also has an e in it. So if I have this e to the negative x, that means that my function had to have an e to the negative x in it. Now, it might have other coefficients, but I had to have that. Now, if I took the derivative of this, it would be e to the negative x times the derivative of that exponent, which is just -1. So that negative coefficient is because of the chain rule. So that's all I need in my original function. Okay? Okay, so 14 is one that maybe you wanted to consult your formula sheet. We haven't used it in a tad bit, but the derivative of tangent is secant squared. So if I have a secant squared there, what did I start with? Tangent. Okay, then I move on to this one. All right, so I have a 1/2. I have x to the 1/2, so I'm going to leave a little tad bit of space there. I add 1 to 1/2, so 1/2 plus 2/2 is 3/2. But then I divide by 3/2, which is the same as multiplying by 2/3. Okay, so then this becomes tangent. Those 2's will actually cancel, or you can leave it 2/6. I don't really care. Reduce it or not. If we reduce it, it becomes a 1/3. X to the 3/2. Tack on the plus c. Okay with that one? All right, so 18. The 3 right here is there because of chain rule. Okay, so I notice that I have a 3x here and I have sine in front of it. So whether it was sine or cosine to start with, I would have had to use the chain rule and multiply by the derivative of 3x, which is why the 3 is there. Okay, so let's just think, ignore the 3. I have a negative sine. What's the antiderivative of just plain sine? Negative cosine. So what if I have a negative sine? That means I started with regular cosine. So f of x had to be cosine of 3x. All right, so let's think about taking the derivative. Derivative of cosine is negative sine 3x times the derivative of 3x, puts the 3 out in front, and then add your plus c. Okay, these will get easier the more we do them. This one is a formula, so if you tried to rewrite that as 1 minus x squared to the negative 1/2, it would have gotten really messy. But if you will look right here, you can see that that's pretty much just the same thing. Instead of a u, there's an x. So this antiderivative is just sine inverse of x. Let's see. Did that one sneak up on you? Okay, is that a formula or should I rewrite it with a negative exponent? This one I would rewrite. Something like that, be on the lookout for formulas, and we don't have many of those. If it's 1 over x, then that's your natural log. But if it's 1 over x squared, that is not natural log. I would just rewrite this as x to the negative 2. And then let's use the exponent rule. So I'm going to add 1 to the exponent. Okay, so that becomes, what's negative 2 plus 1? Negative 1, but I have to divide by that exponent. Okay, antiderivative of negative 1 is negative x, and then there could have been a constant. So you can leave it like that or change it to negative 1 over x minus x plus c. This negative I just wrote out front. X to the negative 1, I made it 1 over x to the positive 1. Remember to check these if you're unsure. If I want to know if that's right, then take the derivative of it. If it gives you that, then you're good. If it doesn't, something went wrong. Okay. Any other questions on those? Okay, so let's go back and finish those notes. Yes. Oh, yes. 3, 4, and 5. Do you want to talk about any of them? Okay. All right. Put that aside. Okay, so let's get the notes back out. We have 2 more things. So left ram, right ram, mid ram, you're okay with that concept. Okay. Let me say this. The table that I gave you, the width of each rectangle was the same because this time difference was uniform, a time difference of 1. Sometimes you will see tables where it's not the same. So it might be like from 0 to 1, and then the next one is 5, then the next one is 8, and they don't use uniform widths. We handle it the same. You just can't put the width out in front like this. You just have to individually do each rectangle. Length width plus length width plus length width, where the widths are different each time. Okay, so just be on the lookout. Sometimes that happens. Okay, so check this one out. Alright, so I'm going to show you how this formula works in a graphing calculator. Very cool, because, I mean, let's face it, this is a small computer, right? So it can make computations way faster than we can write out a bunch of length widths. So this is our function, x squared times sine x. You might not know what that looks like. I don't think I would offhand. This is the graph of it. And we're only interested on the interval 0 to 3. So if you'll notice, this is our domain, and this is our range, this little screenshot that is on here. Okay, so this is 1, this is 2, this is 3, and this is going up to positive 5, so 1, 2, 3, 4, and 5 there. So that gives it a little bit of scale. All right, so imagine this, that I ask you to make 100 little rectangles here. Like, it would take us forever. It would be so incredibly tedious. And then to not only do left ram, but right ram and mid ram as well. Like, we'd probably be here for the rest of the day figuring out all that. So here's where our nice little program comes in. I hope it's on this one. It's not. It's on my other one. Let me grab it. And then I can link calculators and transfer them to your calculator so that you don't have to type the program in by hand. Okay, so what we'll do is we'll end up putting this program, there's a program key on your calculator right here. Has anyone ever tried to program it with anything at all? Okay, so some of y'all have played around with it a little bit already. Okay, so the first thing you want to do is go to y equals and type in the function that you're dealing with. X squared sine x is the equation. Okay, then I'm going to go to program, and it is my sole program there. So RAM stands for rectangular approximation. I'll send you the video, and good luck. Run like the wind, bullseye. Okay, so I'm going to choose the RAM program and push enter. So this is asking you for A. What does A represent? What would you think? It's going to find the area. That's going to be called subintervals. It's going to be the low end of the X. So because I want to go from 0 to 3, I'll type in 0, enter. Now it wants B. That's the upper boundary of your X. Now it wants the number of subintervals. So I'll just start with 5 here. And watch this. There you go. It's done. I got left, mid, and right. So I would type in, I'm not going to do every single one of these, but I'll do a few just so you can see how impressive it is, and then in a minute I'll work on transferring to yours. 5.916. So you can see that the left RAM is pretty, I mean, that's a pretty significant difference there. Mid RAM, notice, is a lot closer to right RAM on this. And it's just, it has to do with the shape of the graph. But generally, mid RAM should be somewhere between these two. Let's do 50. Now, as you get into these larger subintervals, it does take a tad bit longer to compute. Okay, so I'm still going from 0 to 3. 50 subintervals. Still not too long, though, is it? Yes, ma'am. Yes, I'll sit back. Okay. Miss Christian wants to see Kason for a second. You know where Miss Armas' office is? Yeah. She said just a second. Okay, so isn't that cool? Like, way better than setting up all those rectangles. Now, notice how close these are getting. I've got 5.736, 5.777, and 5.812. Those are definitely getting closer. Let's just do 100 and see if we can approximate what the actual area was, because the more subintervals we get, the more accurate this should be in terms of what the real area would be. Okay, from 0 to, oopsie. What happened? Don't need that. There we go, 0 to 3. Let's do 100 subintervals. Need a little Jeopardy music. There we go. Ooh, very close now. 5.757, 5.776, and 5.795. So it's definitely, I would say, 5.7 something, right? For the actual area. So it just lets you zero in closer and closer to the actual area. So now that was considerably far from the actual. That one was closest. And so, you could do 1,000, keep going until you can get a pretty accurate estimation. To my knowledge, I've never seen an AP exam question that involved this on your calculator. It's just kind of cool to do. So, not a necessity to have it on there. It's just sort of a fun little toy. Okay, last problem. A sphere is obtained by revolving the curve. Hello.
Can I ask you a quick question?
Yeah. I've got video running. It's not top secret, is it?
No. I'm just trying to figure out which. Do you remember who's going which room?
Oh, Lord.
Does it matter?
Oh, it mattered to some, yes. I think Harper.
Or this one of those.
Yes, I think it was. Where's the bathroom? Right there? Maybe he wanted that one. It was important that he was near a bathroom, he said. And then I think it was, or maybe it was Harper, Clark, me. The guy's name, they cared a lot more than I did.
I'll go see them. Okay. All right.
Okay. And where are you going to be during breaks? I have something I want to run by you. Okay, just swing by here.
Mr. Brown's gone, so I think I got to.
Oh, okay. I'll catch up with you later. Okay, sphere is obtained by revolving the curve square root of 16 minus x squared about the x-axis, where x is measured in inches. Estimate the volume of the sphere by partitioning from -4 to 4 into 8 subintervals of equal length, slicing the sphere with planes perpendicular to the x-axis, such that each cross-section is a cylinder of equal height. Use right ram to estimate the volume by using right-hand endpoints. Would the estimation using left ram or mid ram be the same as the right ram estimation? Then compare your answer to the answer obtained by using the volume formula for a sphere. You got all that?
No.
Okay. All right. Now, I know full well that we have a formula for volume of a sphere, and it is right there. So I could figure it out using geometry. But this is a way of using calculus to approximate volumes that maybe aren't a nice shape that we already have a geometry formula for. There's a homework problem that you're going to do, like the nose cone of a jet, which is more like it's called a paraboloid, like a three-dimensional parabola. And that calculus is a more accurate way of finding the volume. So we're just doing it on something that we do already have a formula for so that we can compare the accuracy of it. Ron, what were you going to say?
So like, if you had like a gourd.
Yes. Yes. Okay.
It sounds weird, but like.
No, it doesn't, and I'm going to show you how you can do that. Okay, so first of all, what is this equation here? Semicircle of radius 4. Okay, so here is our semicircle right here. Okay, so that equation is square root 16 minus x squared. Okay, so what we're going to do, imagine that I take this little semicircle and like shade it in below so that I truly have the whole semicircle, and I'm going to revolve it around the x-axis. And so what would be filled in is a sphere.
Yes.
Okay. I'm going to use some calculus here, some right RAM specifically, to estimate the volume of this sphere. Ah, yes. Okay, so what I'm going to do is take this and slice it perpendicular to the x-axis. So that each slice, it's kind of easier for me to see if I turn it, each slice is a cylinder. Now, the more slicing I do, the thinner the cylinders are and the more accurate my estimation would be. The chunkier those slices are, the less accurate it would be, just like with the rectangles that I talked about yesterday. Okay, so for simplicity's sake and time's sake, we are slicing this into 8 subintervals. So I have 1, 2, 3, 4, 5, 6, 7, 8 cylinders. Okay, how tall is each cylinder? When I say tall, think of it as turning it. How tall is this here? It's 1 for each one. How do I know? Because I'm going from -4 to 4, and I'm slicing it 8 times. So that's a distance of 8. 8 slices means that each width is 1, or if we're talking about a cylinder, that's really referring to the height of the cylinder. Okay, here's our formula for finding volume of a cylinder. Pi r squared h. So we've already established that h is 1. H is 1. Now, tell me about the radius of each cylinder. Again, it kind of helps me to turn it this way. Is the radius of each cylinder the same? No. It's thickest in the middle here, thinnest or smallest out here at the ends. How do I determine what that radius is?
From the x-axis to the top of wherever the cylinder meets.
The function, yes. So my slices, this is sort of a little two-dimensional depiction here. So my slices, this is actually the radius, what I'm drawing right over here. In the middle, that's where the radius is largest, and I know the radius right there is 4. But as I move along here, the radius gets smaller, and if I'm at the very end, the radius is 0. Okay, so if I'm over here, we're using right RAM. So I'm going to start with 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I'm going to start on the right endpoint. So right there, I'm going to use that to determine what the radius is. What is that number? Let's actually just draw a number line. Here's 0. 1, 2, 3, 4. And then 1, 2, 3, 4. This is where this cylinder is hitting the x-axis, so to speak. Okay, so I have a slice, 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 slice. Okay, so I'm going to start here for right RAM. I'm going to use 1, 2, 3, 4, 5, 6, 7, 8. If I used left RAM, I would start with the first one and stop there, which in this function I would get the same answer, wouldn't I? Okay, so right RAM, this is going to be my first radius, which is over here at -3. the height of that little segment right there is the radius. How do I know what that is? It's whatever I get if I sub 3 in the function. Moving along, I would sub -2 in the function. I would sub -1 in the function. 0, 1, 2, 3, 4 to get the radius. Okay, so this is how I'm going to calculate the volume. It will be a whole bunch of cylinder volumes added up. Okay, notice that pi is in each and every one. Height is 1. The only thing that changes is the radius. Okay, so for the first radius, I'm going to use 16 minus -3 squared times the height. Okay, so this right here is pi r squared times the height. And we have to do it 8 times. Okay, but look what happens when I square that square root. No, we've got eight subintervals. Oh, do half and then double? We could do that. I'm probably going to set them all up just so that you can see all 8 of them. But yes, you could do that. Only because it's symmetric on both sides here. If it was something wonky like that previous graph, then I couldn't do half and double. Okay, so the square root and the square, that's just going to cancel, right? So what is 16 minus 9? 7. So that's really just going to become 7. But I'll change it in the next step. Okay, plus pi r, so the next one will be at -2, squared times height, plus pi r is 16 minus -1 squared, times height. So that's 3 plus pi square root 16 minus, okay, see, -3, -2, -1, the next one is 0.
Could you factor it out?
Yes, if you wanted to, you could bring the pi and the height, which is 1, out in front of all those. Times 1. Okay, the next one. 16 minus 1 squared. Next one. 16 minus 2 squared times the height. That's 1, 2, 3, 4, 5, 6. Here's 7. 3 squared. And the last one, 16 minus 4 squared. Okay, so that should give us 8 different cylinders that we're taking the volume of and adding them up. And Lord, I would not go to my calculator right now because this can be simplified so much. Okay, so 16 minus 9 is 7. But it's the square root of 7, but when I square it, I just get 7. So this is 7 pi for that first term. Okay, the second term, 16 minus 4 is 12. Square and square root cancel, so that's 12 pi times 1 is just 12 pi. Okay, 16 minus 1 is 15, so that's going to be 15 pi. Okay, that's going to be 16 pi. Yeah, and then we start going back down again. 15 pi. 16 minus 4 is 12 again. That one will be 7 again. And then the last one actually does have a radius of 0, so we just have nothing there. So it's 1, 2, 3, 4, 5, 6, 7, 8. Okay, let's see. I've got How about if we do that? And then add in the 16. Okay, so I've got 7 times 2 is 14. 12 times 2 is 24. 15 times 2 is 30. And then 16 off there by itself plus 0, of course. How much? 84 pi? Okay. And that would be cubic, whatever. I don't think we had any units. Oh, it is in inches. Cubic inches. Okay, so let's try now the volume formula of a sphere and see how close this is. So volume of a sphere would be 4/3 pi r cubed. And let's see what that gives us. I'm going to not multiply the pi since I already have pi by itself over here. So I'm just going to do 4/3 times 4 cubed is 85 1/3 pi. It's pretty close, isn't it? For a rough approximation, it's not too far off. So yeah, if you had a gourd, then you could treat it this way. Now what you would need is the different radius or a function to use. Okay? Question? Alright, I think that is the last. Yeah?
I was going to ask you about the parabola again. I was like,
The,
but even if you did double the radius, it wouldn't work.
on a parabola,
Yeah.
right? Because it's not symmetric. Okay, so that's it for the notes. So what I want you to do, you've got a good bit of time, is work on those homework problems, or start them, or finish them. We are adding just 2 to yesterday's. So it's the same as yesterday's, but add in number 11 and 13. One of them is using the program on your calculator. So I'll come around and link those, or as I get a couple linked, I'll let you link to each other as well and transfer those programs over. Okay. After I finish doing that, if you've already started and you have some questions on homework, I'll come and answer those too. Yes, please. Stop this recording.